Hi, so welcome to the 10th lecture in the Jabrah Statistical Machine Learning series. And today we're gonna start talking about what we call the binomial distribution. So to define this distribution, we actually need to build on top of the results that we actually got from the Bernoulli distribution. So if you haven't, please watch the previous lecture because we'll just be continuing from there. So in that lecture, we gave an example of tossing a coin where we said that we define an event x and x can take two values with the heads or tails. Like so a random variable x, right? And which represents the event of tossing a coin, and it can take two values. So we said x was an element of 0 or 1, right? And we defined a probability of getting heads and the probability of getting tails that was parameterized by mu. And our results from the previous lecture was that the mu under the maximum log likelihood estimate for the binomial distribution was given by n is equals to 1 until n of xn. This is what we defined the mu under the distribution to be. So one thing already is we can, instead of writing this in this form, we can actually define the number of times. Like let's say we flip a coin 5 times, and then we denote the number of times that we get heads, right? Because we say it's the probability that x is equals to 1, right, given mu, which was equal to mu. We said this is the event where we have x equals to 1, that's when we get heads. So we can define the number of times we get heads if we try this experiment 5 times by m, right? So the number of times we get heads, we can parameterize it by a value m. And if we define the number of times we get heads by m, then we can rewrite mu ml to be equal to m over n, right? Because this is the number of times that we get heads over the number of times that we run our experiment. So let's say we decide to flip a coin 5 times and we get heads 5 times, right? So which means that n is equal to m is equals to 5, right? Then this means that the mu under the maximum log likelihood estimate will be equal to 1, right? So 5 over 5 is 1. And this this is from a frequentist point of view. We are predicting that all future observations from this experiment will give us a mu of 1. And we know, like from that this obviously doesn't make any sense. And this is just an example whereby we are overfitting because we're using like maximum log likelihood estimate here. Probably if we carry out this experiment many more times, like we'll approach the true value of mu. But given that this is the limitations of our experiment, that's why it would be advisable at times introducing a prior that would not lead to such an extreme estimate as to what the value of mu is. Yeah, this is something we actually talked about before in the like in one of the earlier lectures. But we're just highlighting it here again so that you truly understand like the motivations as to why we introduce priors, right? So having said that, so Yeah, back on topic about the binomial distribution, we are trying to, here we're just trying to work out the distribution over values of m. What that means is we flip a coin 10 times, and let's say we see, so out of those 10 times, uh, how many times are we going to get a heads, right? Let's say we get the heads like 2 or 3 times, right? So what's the probability of getting a head 1 time, 2 times, 3 times, 4 times, all the way up to 10 times? We can form a distribution over that. A more visual example of what I mean is, say that we have, we can have something like this. So where we defined m, and it can take values of 0. M is the number of times that we're getting heads. So let me actually write that clearly, that this is the number of times we are getting heads. Okay, so how many the probability that we don't get heads at all, the probability that we get it once, the probability that we get it 2 times, 3 times, 4 times, all the way until say 10 times, right? And maybe this is the probability here, right? And this is the value of m, and this is just the probability. It could be 0.1, it could be 0.2 here, it could be 0.3 here, and we could have say n is equals to 10 and mu is some value, I don't know, 0.3 or whatever value it is. So this distribution over m, right, which is the number of times we're getting heads, is what we call the binomial distribution, right? And to understand it better, as you can see, based on the way that we're conducting this experiment, this is just building on top of the distribution we looked at in the previous lecture, which was the Bernoulli distribution. And now we say that this binomial distribution is defined as follows. So the binomial distribution of m, right, because this is the key variable here, given n, the number of times that we're conducting this experiment, and our mu, this is equal to n choose m times mu to the m. This is, so we're already familiar with this from the Bernoulli distribution, so there's no need to explain that. But we say n choose m here to indicate something important, right? So this is essentially saying, let me use this color for consistency. So how many ways of choosing m objects out of n identical objects? That's what n choose m is. So basically we're asking questions like, okay, given n is 10, how many ways are there of me getting like 3 heads? This is essentially what this question is, and multiply the ways that you can get this by this mu m times 1 minus mu n minus m, right? This is our probability distribution over this. So we can find n choose m, like this is actually expressed as n factorial over n minus m factorial m factorial. That's what this expression boils down to. If you want to actually find the value of this, which is all good and fine. But now we need to prove certain aspects, or we need to prove that, well, we're given this, we need to prove that this is actually a probability distribution that sums up to 1. And we need to think about, once more, how do we find the expected value under this distribution as well as the variance. So these are the two things we need to think about. So first, we need to prove the following, that the summation from m is equals to 0, let's use m, not n. So from m is equals to 0 until n of m choose m mu to the m times 1 minus mu to the n minus m is equals to 1. So this is the proof we're working towards. Right, so we need to prove that it's a probability distribution, but first, to aid in this proof, we're gonna need to prove a couple of properties that are gonna help us complete this proof. And the first one, so let's say property 1 would be that n choose m plus n choose m minus 1 is equals to n plus 1 choose m. Right, so this is the first property we need to prove, and in order to do that, well, let's actually work it out. So let me use a different color for that. So this is equal to n factorial. Okay, maybe this color is not so clear. Okay, let's use blue. So this is equal to n factorial. Sorry, also don't like this one. Okay, I'm gonna just stick to it. So we have n factorial over n minus m factorial times m factorial plus n factorial. So this is actually referring to this term, and this is this term, right? So this is n factorial over, so if instead of m we have m minus 1, so this is n minus m, so this is n minus m minus 1, but if you multiply it out, it becomes n minus m plus 1 factorial times m minus 1 factorial. So now we need to prove that this would give us that, right? So let's actually do that. So our common denominator here is m factorial times n minus m plus 1 factorial, and then we need to write our numerator. But before doing that, we need to keep something in mind that might help with our proof, and that's the following, that x factorial is equal to x minus 1 factorial times x, right? So this is something that we should be aware of, because we're going to continuously use this property in our proof. Okay, so let's start. N minus n factorial into n factorial into n factorial cancel out. N minus n factorial into n minus n plus 1 factorial. This gives us n factorial, which is here, times n minus m. So where is n minus m coming from? Well, we're using this property where we say n minus m plus 1 factorial divided by n minus m factorial should give us n minus m, right? So that's the property we're using here. So this x factorial divided by x minus 1 factorial. So instead of x, just substitute n minus m, and you'll find the same answer. And then we do the same this side, and we get plus n factorial times m, right? And this is equal to n factorial times n minus n factorial times m plus n factorial times m, all of this divided by m factorial n minus m plus 1 factorial, and this leaves us with n factorial times n over m factorial n minus m plus 1, which is equals to n plus 1 factorial over m factorial times n plus 1 minus m. I'm writing in this way so that it's very clear that this is actually equal to n plus 1 choose m, right? So we've proven this property here. Let me highlight it in blue. We've proven our first property on here, because we reached this answer. So because we've proven this property, that means we're gonna make use of it during our proof. Okay, so moving on to our second property. See if I can write this in magenta. So our second property, so I'd like to call this property 2, is as follows. It says 1 plus x to the n is equal to the summation from m is equals to 0 up to n of n choose m times x to the m, right? So this is our second property that we're trying to prove. And by the way, this is called the Binomial Theorem, right? So this is the second property we're trying to prove, because again, the reason we're doing this is so that they can aid us in this proof. So this is what we are trying to prove, like this summation over here. So let's move on to the second property. So how do we prove this? So we're going to do a proof by induction, right? So when n is 0 and n is 1, we can easily substitute these values and see for ourselves why this holds to be true in this case for values of n is 0 and then values of n is equals to 1. So we have our base case already. So what we need is to define our inductive. So we need to define our inductive or hypothesis step. And for this step, what we are actually trying to prove is that we will assume the following. We will assume that 1 plus x to the n being equal to the summation of, usually for this we use the value of k, but I'm just going to use n here. Should be easy to follow through. I mean, we use a constant k, the value of k. So n choose m to the x to the m. So we're going to assume this holds true, right? So we're going to assume that this holds true, which means we are trying to now prove that, well, in our inductive step as well, that let me use maybe the same color, 1 plus x to the n plus 1 we're trying to prove that this should give us summation from m is equals to 0 up to n plus 1, the inductive step, n plus 1 choose m of x to the m. So if we can prove this just by assuming this hypothesis to be true, and we already have our trivial base cases defined, if we can prove this, then that means, well, this property is actually true, at least by induction. Well, I'm not gonna cover the details of how to do proofs by induction in this lecture. If you're not familiar with them, I guess you can just do a simple Google search. They should be pretty simple to follow through. So, well, it is like the basics of them. Okay, so we know that 1 plus x to the n plus 1, we know that this is equal to 1 plus x times 1 plus x to the n, right? But we're assuming that 1 plus x to the n is true. This is what we're assuming. We're assuming this is true, which means that this is actually equal to 1 plus x times, since this is true, that's summation from n is equals to, since this is assumed to be true, I should say, up to n of n choose m x to the m, right? So now let's just multiply out these terms. This is like equal to the summation from m is equals to 0 until n of n choose m to the xm, so we multiply this by 1, plus x multiplied by the summation from m is equals to 0 up to n of n choose m x to the m, right? So now we need to multiply out this x inside this summation, and we end up with the same thing we have here, plus summation from m is equals to 0 until n of n choose m x to the m plus 1, right? This is what we do. This changes in m plus 1. But now here we perform a little trick. So instead of writing it in this manner, let's see. Yeah, we can write it like, especially the second term. I mean, the first term we can leave it as is. M is equals to 0 up to n of n choose m to the xm plus the summation. Now we're gonna change the limits here, right? So we're gonna change them and say, actually, let me use that green. M is equals to 1 until n plus 1, right? The limits have changed, so that's why I'm indicating it in green, so that it's very careful. And then we have n choose m minus 1 x to the m. So this is actually like what we see here. This over here, it's actually the same as here, okay? These two things are the same. And you can prove it to yourself by actually fitting for m is equals to 0, this will be 0 and this will be 1. For m is equals to, which is the first term we encounter when making this iteration, but when m is equals to 1, this is 0, which is the same as the 0 here, and this is 1. So these are actually the same things that we have here. So this is same, right? Okay, so we change the limits of our summation, but the next thing we're going to do is, okay, we have these two terms. Now, when are these two terms equal? The only time that these two terms are actually the same, like what are the common indices? So if I say the common indices between these two summations, is between m is equals to 1 and m is equals to n. So that means between m is equals to 1 and m is equals to n, we can actually combine these two things, right? Which means we can actually say summation from m is equals to 1 until m is equals to n of, let me use a different color for this indices to make things clear. M is equals to 1 until n. Because these are the common indices, we can use the summation and we can combine these terms. Say n choose m, x to the m, plus n choose m minus 1, x to the m. But because we did this, there's something we need to take care of here, and that is when m is 0 and when m is n plus 1, right? These are the two terms we're missing in our summation. So we need for when m is 0, this is actually n choose 0, right, times x to the 0. That's the value when m is actually 0, and when m is n plus 1, when n is n plus 1, this is actually n choose n plus 1 minus 1, which is n, times x to the n plus 1. Alright, so this is the value when n is n plus 1. So now that we have defined these two limits, the next thing we need to do is as follows. We know n choose m times n choose m minus 1. Well, we've proven this property already here. N choose m plus n choose m minus 1 is n plus 1 choose m. So we can combine these two terms here, right? And if we combine them, we end up with, by the way, okay, let me just do this first. Summation from, once more, m is equals to 1 until, oh sorry, I was using blue. Okay, summation from m is equals to 1 until n, this for this spot, of what? n plus 1 choose m, so we can combine these two terms, times xm, plus, okay, so here with n choose 0, but what we can do is rewrite this as n plus 1 choose 0 of x to the 0, because n plus 1 choose 0 and n choose 0 are actually the same thing, though what boils down to 1 anyway. And n choose n is also the same as n plus 1 choose n plus 1 of x to the n plus 1. So this is x to the 0. Okay, now that we have everything in terms of x plus 1, we can add this term back in, and we can also add this term back in, and we'll have a summation from our proper indices m is equals to 0 until n plus 1 of n plus 1 choose m of x to the m, right? Because we added this indices back in, and by that we have proven this property, right? And in that sense, we have proven the binomial theorem to be true. So this is the basic proof of the binomial theorem. And so the next step now to actually complete what we're doing here is to, again, okay, let's go back to the original objective. We're doing all these things, but we have an objective, which is to prove that this, binomial distribution formula sums up to 1. And to do that, we come back to say summation from m is equals to 0 until n of n choose m to the mu m by 1 minus mu to the n minus m right, by 1 minus mu to the n minus m is equal to 1 minus mu to the n times the summation from here I took out 1 minus mu to the n. Summation from m is equals to 0 until n of m choose m times mu to the m 1 over 1 minus mu to the m. Right, so this is where we are. So I just took out 1 minus mu to the n and we're left with this. But we look at this. This actually looks very, well, actually, let me write it in its proper form so that we can see it much clearer. If we say 1 minus mu to the n times the summation from m is equals to 0 until n of m choose m mu over 1 minus mu to the m. Right, this, if we look at the binomial theorem, we say that n choose m x m, this is just 1 plus x to the n. Our x to the m here is just this term u over 1 minus mu to the m. So we can write this as, by following through with the binomial theorem, we can write this as 1 minus mu to the n times 1 plus mu over 1 minus mu to the n. And we make this step by using the binomial theorem, just to make things clear. Theorem, right? The binomial theorem that we've just proven. Okay, so let's simplify this. If we simplify this, we end up with 1 minus mu by 1 plus mu over 1 minus mu to the n, which is equals to, let's expand these terms out, 1 plus mu over 1 minus mu minus mu minus mu mu over 1 minus 1 minus mu to the n, right? We just multiply out each and every one of those terms, and this should give us 1 plus mu over 1 minus mu times 1 minus mu. We're just collecting the similar terms here and factoring out 1 over 1 minus mu minus mu, and these two cancel out and the mu's cancel out, and this is equal to 1. So we have actually proven that this, this actually sums up to a value of 1. Okay, great. Moving on. So from this, yes, we've proven a couple of things, but we had to make use of a couple of properties to help us in making that proof. And finally, we want to prove that the expectation, we want to find the value for the expectation and the variance under this distribution. So what I'm going to do is I'm going to work through with you as to how to find the expectation, and I'll just leave the variance as an exercise so as not to make this video too long. So let's start. So the expectation of m, well, we know what it is in terms of a formula. We just need to take the original term, multiply it by m, and find n choose m of mu m times 1 minus mu n minus m. Okay, so that means we're taking the derivative. Oh yeah, so to be able to actually find this expectation, what we need to do is we need to take our original term, where we say our result from the previous slide, or previous page, not using slide here. M is equals to 0 up to n. So this is what we said, times mu to the m, 1 minus mu to the n minus m. We said this was equal to 1. So what will aid us in finding the expectation is taking the derivative with respect to mu on both sides, right? So we take the derivative with respect to mu here and derivative with respect to mu on the other side. Obviously that side value should be 0, and on this side what we end up with is the summation from m is equals to 0 up to n of n choose m, okay, by. So now we need to take the derivative of this term here, and what this gives us is something of the sort like, well, the derivative of this times the original if we're using the product rule, so that's m mu to the m minus 1 times 1 minus mu to the n minus m plus the original, which is mu to the m, times the derivative, which is n minus m, and we need to use the chain rule here as well, times 1 minus mu times that's 1 minus mu to the n minus m minus 1 times the derivative of what's inside, which is minus 1, right? And all of this is equal to 0. Okay, so if we start expanding it out, we end up with this situation. So we've got summation from m is equals to 0 until n of, we take out this m, times n choose m, right, times mu m times 1 minus m, 1 minus mu to the n minus m, right? But because we took out, this is actually the value of this is mu to the m minus 1, but I put mu m here, so I need to keep this term as well. I need to multiply this by mu minus 1, so that if we multiply these two terms, we get this mu m minus 1. So that's why I'm keeping this there. And this is equal to, and on the other side we have summation from m is equals to 0 up to n of n choose m to the mu m times n minus m times 1 minus mu to the n minus m minus 1. Okay, so already we can see something here. The term here in the term over here that we see in black, this is actually just expectation of x, right? As defined here. That's how expectation of x is defined. So we just need to divide both sides by mu, right? Which means we end up with the expectation of x being equal to, we're gonna take this mu to the other side, right, here, and we're gonna have the rest of it, which is summation from m is equals to 0 until n of n choose m times mu m n minus m 1 minus mu to the n minus m minus 1 which is equal to mu times the summation from m is equals to 0 until n, right, of mu m 1 minus mu to the n minus m over 1 minus mu, because if we do 1 minus mu to the n minus m divided by 1 minus mu, we'll get 1 minus mu to the n minus m minus 1 by just using the rules of indices. This should be clear, and we multiply this by n minus m, right? So this is what expectation of x is equal to. Okay, let's keep going. So that means the expectation of x is equals to mu over 1 minus mu. We can take this mu out because it doesn't depend on the summation terms here, times, okay, what have we got here? Our same summation, then we're going to multiply these two terms out. So that's yeah, I probably need to give myself more space here because this expression is probably going to get really long. So I'm going to say e to the x is equals to mu over 1 minus mu times the summation from m is equals to 0 until n of n times n, choose m, mu to the m, 1 minus mu to the n minus m, minus the summation from m is equals to 0 until n of m, n, choose m, right, I'm just multiplying out these two terms, times mu m, 1 minus mu to the n minus m. So what do we see about these terms? Well, this is just the expectation of x, and if we take n out, this is just equal to 1, right? So we end up with expectation of x is equals to mu over 1 minus mu times n, this is n, minus the expectation of x, right? Which means that expectation of x is equals to n mu over 1 minus mu minus the expectation of x times mu over 1 minus mu. So we take this that side and we end up with expectation of x being equal to 1 times 1 over 1 minus mu. This should be n mu over 1 minus mu. Okay, we're adding these terms up, which means expectation of x is equals to n times mu. Right. So we've proven what the value of this is. So I hope you are able to follow along with the steps we're taking here. But in case you're having any troubles, just pause the video at any point in time, or just try to understand each step as you take. Like if I skip a step that would help you understand, try to figure out what the step might be. But I think this should be, at least the arithmetics of this should be pretty straightforward. And finally, the variance of, well, I say x here, but it's actually m, but in any case, this is equal to n mu times 1 minus mu. So I'm not actually gonna go through the proof for this, but the hint for you is also given in the Pattern Recognition and Machine Learning book by Christopher Bishop. The hint here is that you ought to just differentiate twice with respect to mu, and if you do that, you should be able to get this result as well, but I'm not going to go through with that. So yes, I'm going to end the lecture here, and I hope you have learned something from it. Oh, thank you.